So I think I mentioned with an overview of the solar system, the sun and the planets in our solar system that orbit the sun, I kind of grouped the planets, so I want to emphasize that. We actually have the four rocky, okay, sometimes they're called terrestrial planets, rocky planets. They're closest to the sun. So I'm hoping that, and we'll talk about these coming up, but this is actually Mercury, this is Venus, this is Earth, and this is Mars. So we have, these are the terrestrial planets. And yeah, there you go. Then after the terrestrial planets, we have actually the asteroid belt. But after the asteroid belt, then we have, I think I called them gaseous planets before. I probably should have used this other name. But the gaseous planets, okay, they are sometimes called, the more than likely, the Jovian planets. And they are Jupiter, Saturn, Uranus, and Neptune. I learned it as my very educated mother just served us 9 pizza pies. And at the time, all right, when I learned it, of course, Pluto was a planet, but Pluto is no longer a planet. It's a dwarf planet. Okay, but let's see. The gaseous planets, one of the things I think is interesting, it's almost like they swallowed a terrestrial planet. So at the core of all the gas giants, there actually is a little rocky stub thing about the size of a terrestrial planet. What else do we have? So here I have the inner, or the rocky planets, okay, the terrestrial planets. Some information about them, Mercury through Mars. This first column I wanted to mention, in outer space, we need to talk about distances differently than just inches and meters and miles even. So one of the thing that's helpful, at least within our solar system, is the distance of an AU, an astronomical unit. We covered, of course, the unit on chemistry recently, and we talked about an AMU, atomic mass unit, which is different than an astronomical unit. So an astronomical unit is something near and dear to our hearts. It's the average distance between our planet and the sun. So 1 AU is the average distance between us and the sun. So that makes sense. Let's see how close Earth is to the sun. Well, 1 AU. How close is Mercury? 0.4 AUs. How close is Mars? Well, Mars is 1.5 AUs. Let's see, what else do we have up here? Oh, we talked about, in Kepler's third law, he talked about orbital periods, okay? And these are all orbital periods relative to Earth. So Earth years, Mercury completes 1 orbit around the sun in 0.24 Earth years. Mars is 1.9 Earth years. So you kind of get the idea there. And then one last thing on this slide is the bottom part of that table then looks at the Jovian planets. So beginning with Jupiter on through Neptune. And here we have how far away they are in astronomical units. Check this out. Neptune is 30 times away from the sun than the Earth is from the sun. That's how that works. Here we have how long it takes for them to complete 1 orbit about the sun. I always think that's kind of neat. So if we pick on Neptune, which takes the longest amount of time, make sure I get this right. Neptune takes 163.7 Earth years to complete 1 orbit about the sun. I just think that's so cool. One more thing, or another thing, before I move on. If I draw kind of a line here, okay, it's separating the terrestrial planets from the Jovian planets, the rocky planets from the gaseous planets. Look with regard to density. If we go ahead and set the density of Earth as 1, notice that the inner planets, actually all the other terrestrial planets, are a little bit less dense than Earth. But check out the density. This means that actually these gas giants, these Jovian planets, are very low with regard to density, and that makes sense. So I mentioned earlier or recently in the video about the sun that we have spacecraft that are dedicated just to studying the sun. And oh my gosh, there are a lot of spacecraft out there that are dedicated to studying the planets. And that's what this slide is all about. You're probably familiar with NASA. That's our Air and Space Agency. And Europe actually has something similar to NASA called ESA. And so this slide, I just kind of caught my eye, not slide, but this figure, it just kind of caught my eye with regard to the cool looking all those spacecraft that the European Space Agency has put out there. And like this says, science, especially I think space science, you have to kind of take your losses with your successes. Recently, actually, the European Space Agency sent I'm not sure if it must have been a type of rover to land on Mars, and it actually crashed into the planet. So, I mean, there's a lot of that goes on. So this one right here, it's a little bit harder to read, but this one is actually NASA's. This one is what NASA's activity is, and it's kind of neat too. It shows, let's see, here we have I'm not sure, I don't want to butcher it, but you just see a lot of different things. Down here, this actually is the schedule. This is in 2014 figure, but here we have kind of where leaving 2016, entering 2017, you kind of see that it takes years and years actually to get these spacecraft prepped to be sent out into orbit. As you might imagine, it's sometimes, well, it's all about timing too. You can't just, the planets need to be in the right position to assist in getting the spacecraft where they want it to go. So I'm going to take you, I think, out to this website right quick. So, but I guess the only thing I wanted to mention that it's actually going to mention, this is the, it's going to mention the ESA mission. So down here, ExoMars, Schiaparelli analysis to continue the fate of the ExoMars lander. Schiaparelli remains uncertain. So, I don't know, maybe it'll come back to life.